So this is G481 homework booklet question 26. We've obviously got our hose pipe here that's spewing the water out. We've got various dimensions. And the first thing to note really is this question here on figure 226.1, draw an arrow to show the direction of the acceleration. A number of people just simply don't do that because they don't see an answer slots, they don't read the question. It really is important that you read every bit of information you're given. Also, as part of that really would come following on from that idea of reading all the information you're given, is the fact that you're told here that you can assume that air resistance is negligible. Well, if air resistance is negligible at this point P, what's the only force acting? The only force acting is the weight. The weight is straight down, therefore the acceleration must be straight down. Hence my answer on the diagram for question part 26 part A, an arrow straight down. Next, we're asked to describe the energy conversion that takes place as the water travels from the end of the hose pipe to the ground. I made a bit of a mess of this when I wrote out the answer, which I only spotted a moment ago, but I've corrected it now. So we start off with gravitational potential energy, and this pencil mark was for the word gravitational. The gravitational potential energy we got at the top, and we've got kinetic energy because it's already moving, and that's been converted to only the kinetic energy at the bottom. So you're not going to get 2 marks just for saying gravitational potential to kinetic. That's one energy transfer, so it's only really 1 mark. So we need that extra bit of information as well to justify that second mark. And in here, it's the fact, in this case, it's the fact that we've got potential and kinetic energy at the beginning rather than just the kinetic energy. We're then asked to explain why the horizontal component of the velocity remains constant at 7 meters per second. Well, that's very straightforward. If we go back to the diagram, my velocity is 7 meters per second horizontally, and the only force we've got acting is straight down. That's perpendicular. A force has no effect on a velocity that's 90 degrees to it if we're just looking at the component. So because it's at 90 degrees to that horizontal component, it's not going to affect that horizontal component. Of course it's going to add in an ever increasing vertical component to velocity as well, but the question was about why it has no impact on the horizontal. So the force, the acceleration, is at right angles to that horizontal motion, is why you remain at 7 meters per second. Now D and E are both show questions. I've highlighted that, and the point about a show question is that you have to be very, very careful to make it clear where things are coming from. We're not getting marks for getting answers, we're getting marks for doing the working. Now I've written out 2 alternatives here. This is our bog standard way of finding out how long something takes to fall from a ground. So we've got initial velocities 0, we've got a height, we've got an acceleration, and we use s equals ut plus a half at squared. If I do that on this occasion, I get that. It's 0.515 seconds, no problem. Now that to me is an awful lot of work for 1 mark, and it was only 1 mark. And the reason for that is actually on this occasion we could look horizontally. We know that horizontally we've got no acceleration, so my s equals ut plus a half at squared just becomes s equals ut. So the time is for displacement divided by the velocity horizontally. Just going back to the diagram, looking at that diagram, horizontally I've got a distance of 3.6 meters. I've got a velocity of 7 meters per second, so it's simply that 3.6 divided by the 7 meters per second, and out pops the answer. Now that looks like a bit of 1 mark working. Really, I suppose ultimately it's for the 3.6 divided by the 7.0. We're then asked to go on and show that the speed of the water when it hits the ground is 8.6 meters per second. I suppose the initial question is, does it mean horizontally or vertically? And if we think about what's going on, there's going to be that horizontal component that is constant. We're also going to have a vertical component, and the speed of the water when it hits the ground is simply the magnitude of the resultant vector of the horizontal and vertical velocities. So the first thing we've got to do is say, well, we know the horizontal component, we know it's not changing, it's 7 meters per second. The vertical component, this is a v equals u plus at, with u equals 0 is simply the vertical acceleration multiplied by the time. 0.514, it's 5 meters per second. Once I've done that, I've got a horizontal component, I've got a vertical component. The size of that resultant velocity is what we're after, and I can do that with a little bit of straightforward Pythagoras. So v squared is 7 squared plus 5 squared is 8.6 meters per second. The key here is, again, as always, to separate out the horizontal and the vertical component. It turns out there are other ways you can get the vertical component of the velocity. You could use v squared equals u squared plus 2as. I'll leave that as something you can try out. But you do have to be very, very careful if you do that, because what you can't do is put in a u of 7. If you put in a u of 7, it happens to give you the right answer of 8.6. But if you're doing that to find out the final vertical component, that's not not accurate physics. Vertically, the initial velocity is u. And so if you're using v squared as u squared plus 2as, that's fine to find the vertical final velocity, the vertical v. But in that situation, you would have a u of 0. So it would just be v squared is 2as, and you could work out the v from there. One way or the other, you do end up with 8.6, and I think that's probably the clearest way of doing it. So that was G481 Homework Booklet question 28. No, it wasn't 26. Sorry about that.